This is Chapter 10, Measuring Instruments. We've already covered this chapter in DC circuits, but we're going to review some of the information here. Section 1 is about digital multimeters. Digital multimeters, or DMMs, they have several advantages over the analog meters. They're more accurate. They have expanded measurement capabilities, meaning they can measure things like frequency, capacitance. They can be used to test diodes and transistors, things like that analog meters are not necessarily capable of. They're much easier to read than an analog meter. We just see the numbers on the digital display. There are lighter loading of the circuit under test with a digital multimeter as compared to an analog type, so we'll see less loading effects of the circuit. The polarity is indicated on the readout. Sometimes the voltage will be read as a negative versus a positive, depending on the polarity that we connect the leads to the circuit as. An analog meter is not necessarily capable of polarity indication. And digital multimeters are auto-ranging. Analog meters, if you're measuring a voltage between 0 and 10 volts versus 10 and 100 volts, you have to set the analog meter to read those voltage values. The digital multimeters do that automatically. This is a photograph of a handheld digital multimeter. This is a photograph of a benchtop type digital multimeter, which is the kind that we use in the lab. This is section 2. It's about analog multimeters, or VOMs. That stands for volt, ohm, milliamp meter. So analog multimeters are typically capable of measuring voltage, resistance, and current, and that's usually about it. Digital multimeters, again, they can measure many more different things. The operation of an analog multimeter is based on the motor action occurring between the permanent magnet's field and the field established by the movable coil when the current passes through it. And so we did cover this in DC circuits, but maybe it makes more sense now. This is a photograph of an analog meter. And so how the analog meter works is we have a coil wrapped around a core material, and that core material is movable. It can rotate, and it rotates against some springs. The springs want to keep the needle pointed all the way to the left. And as the current passes through this coil wrapped around this core material, we get a magnetic field set up. And the magnetic field is set up in such a way that the north poles will repel each other, the south poles will repel each other, and the needle will move to the right. And so again, that magnetic force is pushing against these springs, and the needle will move to the right and indicate to us the voltage or the current. This is a simplified version of that circuit. Permanent magnetic field north and south. As the current passes through the coil, we set up a north and south pole around the coil, and the needle will move against those springs. So the higher the current in the coil, the stronger its magnetic field, and the further the coil is moved. So more current or higher voltage, which results in more current, means a stronger magnetic field, and the coil turns farther, and the needle indicates a higher voltage or current. This depends on DC and the direction of the current in the coil. This does not work in the reverse polarity. If the polarity of the current passing through the coil were to change, we would get a south pole at the top and a north pole at the bottom, and the needle would try to bury itself below zero. So the polarity in an analog meter is very important. The coil moving induces a current which dampens bounce or overshooting. And so what that means is that as the current passes through the coil, we set up a magnetic field, and the coil wants to start to rotate. As the coil rotates, the turns of the coil cut the magnetic field as they rotate, which induces a counter voltage, which slows the flow of the current, and therefore the needle of the meter does not overshoot and then bounce until it finally settles on some value. So as the needle moves, that counter EMF dampens out any bounce, and the needle makes a nice smooth action. Section 3 is about the voltmeter loading effects. And again, we covered this in DC circuits. We'll review some problems here in just a second. Voltmeters are connected in parallel with the components that they are measuring. So when you measure voltage, you connect the leads of the voltmeter in parallel to the resistor or whatever the component is that you're measuring the voltage across. The finite resistance of the voltmeter alters the circuit conditions. The higher the resistance of the voltmeter, the less loading effect it has on the tested circuit, resulting in higher accuracy. And so we've looked at circuits like this before, and we'll look at a couple here again. Here in this example, you see that the source voltage is 10 volts. The resistances are equal, and they're in series, so we expect the voltage drop on each resistor to be about 5 volts. When we add the voltmeter to the circuit, though, we are adding a third resistor in parallel to one of the resistors. which lowers the overall effective resistance of this parallel combination, and the voltage drop indicated on the voltmeter is less than we expect. So in this example, instead of being 5 volts, which is what we expect without the voltmeter in the circuit, we may read something like 3.33, and that's because, again, the voltmeter has resistance and it's not infinite. If it was infinite, we would expect to read 5 volts, but because it's not, we expect to read something less than that. In this example, we have a series circuit. R1 and R2 are both 10 mega ohms, and the source voltage is 10 volts, and we're going to measure the voltage across R2. And we know, for example, that the internal voltage of the voltmeter is, let's say, 1 mega ohm. And so in this example, the resistance of the voltmeter is much less than the resistances that we're trying to measure the voltage across. And so if we were to analyze this circuit, the question is, what voltage will the voltmeter read? If we're to analyze the circuit, we need to start by finding the total resistance. And so R2 is in parallel with the voltmeter. We will combine these two first. The resistance of R2, which is in parallel with the meter, will be, I'll use product divided by sum. So that'll be R2 divided by the resistance of the meter, divided by R2 plus the resistance of the meter. And so we will have 10 mega ohms times 1 mega ohm, divided by 10 mega ohms. And so I'll use my calculator here. 10 mega times 1 mega is going to be 10 times 10 to the 12th, which is tera. That'll be 10 tera ohms squared, because it's ohms times ohms, divided by 10 plus 1 is 11 mega ohms. And so if we take this 10 times 10 to the 12th, or tera, 10 tera ohms, and we divide by 11 mega ohms, we get, I'll write it down here, R2 in parallel with the meter will be 909 kilo ohms. So slightly less than 1 mega ohm, right? When two resistors are in parallel, the total resistance should be less than the smaller of the two resistances. And so now the total resistance, this combined resistance in series of R1, so the total resistance will be R1 plus R2 is in parallel with the meter. R1 is 10 mega ohms, and we will add to that 909 kilo ohms. And so when we add these together, we're going to get 10.909 mega ohms. Right? So that's the total resistance of the circuit. Now we'll find the total current, which would be the source voltage divided by the total resistance. Source voltage is 10 volts. Total resistance is 10.909 mega ohms. And so 10 volts divided by 10.909 mega is going to be 916.7 times 10 to the negative 9th, which is nano. This will be nano amps. That's the total current in the circuit, and so I'll write it here, 916.7 nano amps. And so that current, that whole current flows through R1, because R1 is in series with the source. So whatever current is flowing through R1 is the same current total. And so the current here will be 916.7 nano amp. And so now we can find the voltage drop on R1. Voltage on R1 will be R1 times the current through R1, which would be 10 mega ohms, times 916.7 nano amps. And so we have our 916.7 nano amps, and we'll multiply by 10 mega. And we're going to get 9.17 volts. 9.17 volts. And so the voltage is 9.17 volts. And so the voltage in R2, because R1's voltage in R2 is to add up to 10 volts, you can see is very small. So 10 minus 9.17. The voltage on R2 must be 830 millivolts. 830 volts. The voltmeter is in parallel with R2, so they'll have the same voltage. And again, it doesn't matter what path we take here. If we go through the voltmeter and then R1, these two voltages add up to 10 volts. Or these two voltages add up to 10 volts, either way. And so that is the answer to the question. The voltage drop on the meter will be 830 millivolts. So we know that without the voltmeter in the circuit, we expect the voltage drop on R1 and R2 both to be 5 volts. But you can see that when we add this voltmeter to the circuit, we're only reading 830 millivolts, less than 1 volt. And that's because the resistance of the voltmeter is so much less than the resistance of the two resistors that we're trying to measure the voltage across. And again, it doesn't matter what path we take here. If we go through the voltmeter and then R1, these two voltages add up to 10 volts, or these two voltages add up to 10 volts, either way. And so that is the answer to the question. The voltage drop on the meter will be 830 millivolts. So we know that without the voltmeter in the circuit, we expect the voltage drop on R1 and R2 both to be 5 volts. But you can see that when we add this voltmeter to the circuit, we're only reading 830 millivolts, less than 1 volt. And that's because the resistance of the voltmeter is so much less than the resistance of the two resistors that we're trying to measure the voltage across. In this example, I've changed the problem so that the resistance of the voltmeter is much larger than R1 or R2. And so R1 and R2, without the voltmeter in the circuit, are in series, and we would expect the voltage drop on each one to be 5 volts. Since they're equal resistances, they should divide the voltage equally. And so we'll analyze the problem in the same way. We'll start by finding the resistance of R2 in parallel with the voltmeter. And I'll use product over sum. That'll be 1 mega ohm, 10 mega ohms, divided by 1 mega ohm plus 10 mega ohms. And so again, 1 mega times 10 mega is 10 tera ohm squared, and 1 mega plus 10 mega is 11 mega ohms. And so when we divide by 11 mega ohms, we get 909, 1 maybe, kilo ohms. Right? Same answer that we had last time, R1 and R2 in parallel, same values, same answer. Now the total resistance is R1 in series with that combination, so this time it'll be 1 mega ohm plus 909.1 kilo ohm. Now in the last example, we had 10 mega ohms plus 909.1 kilo, and so this time it's 1 mega plus this. And so now when we add, we will get 1.909, maybe the 1 there, mega ohms. So now our total resistance in this example is 1.909 mega ohms. So now we find the total current, which will be 10 volts, divided by the total resistance, 1.909 megas, into 10 volts, divided by 1.909 mega, will be 0.238. That'll be microamps, 5.238 microamps. So that's the total current. And that'll be the same current R1, since R1 is in series with the source. Here we will have 5.238 microamps. Now we can find the voltage drop on R1, which will be the resistance, 1 mega ohm, times the current, 5.238 microamps. And so we'll have 1 mega times 5.238 micro, and the voltage drop will be 5.238 volts. And so the voltage here is 5.238 volts. Now the voltage on R2 has to add to the voltage on R1 to be 10 volts. That's Kirchhoff voltage law. So 10 minus 5.238 is going to be 4.762. So the voltage from R2 is 4.762 volts. And parallel with the voltmeter, they'll have the same voltage, 4.762 volts. And so here in this example, you see that the resistance of the voltmeter is 10 times larger than the resistance we're trying to measure the voltage across. And our answer, though it's still not 5 volts, it's much closer than we saw in the previous example. So the larger the voltages of the voltmeter, the more accurate our voltmeter reading will be. So the voltage from R2 is 4.762 volts. Parallel with the voltmeter, they'll have the same voltage, 4.762 volts. And so here in this example, you see that the resistance of the voltmeter is 10 times larger than the resistance we're trying to measure the voltage across. And our answer, though it's still not 5 volts, it's much closer than we saw in the previous example. So the larger the voltages of the voltmeter, the more accurate our voltmeter reading will be. In this example, we have R1 and R still in series, still equal resistance, 7 mega ohms. And so again, without the voltmeter in the circuit, we expect each resistor to have 5 volts across them. But when we put the meter in the circuit, we measure a voltage of 0.3 volts. And so this time we want to know, well, what is the internal resistance of the voltmeter? And so what we know is that the voltmeter is in parallel with R2. Therefore, they must have the same voltage. So the voltage over here is 4.3 volts. And the voltage on R1 has to add up with R2 to be 10 volts. So the voltage drop on R1 must be 5.7 volts. Alright, so the 5.7 plus 4.3 is equal to 10. Now the currents in these resistors. Current in resistor 1 will be the voltage, which is 5.7 volts, divided by the resistance, which is 7 mega ohms. And so when we divide 5.7 volts divided by 7 mega ohms, we get 814.3 nanoamps. We can also find R2. Here we'll have 4.3 volts divided by 7 mega ohms. And so 4.3 volts divided by 7 ohms is going to be 614.3 nanoamps. Notice that the current in R2 is less than the current one because the current flowing through R1 would have split, and some of it flowed through the voltmeter and some of it flowed through R2. And so R1 is the total resistance of, the total current with R2 and the voltmeter. So the current in R1 has to be the current in R2 plus the current in voltmeter. So whatever current flows here plus whatever current flows here come together to form the current flows in R1. So that's what this says. We want to know what the current in the voltmeter is, so we'll subtract IR2 from both sides. The current in the voltmeter will be equal to IR1 minus IR2, which will be 14.3 nanoamps minus 614.3 nanoamps. And the current in the voltmeter then will be, well, 814.6 nano minus 614.3 nano is going to be 200. I made a mistake typing there. It's 200 nanoamps. 200 nanoamps. The current in the voltmeter. 200 nanoamps. So this 200 nanoamps plus the 614.3, they join together and add up to the 814. Now we can find the voltage drop in the voltmeter. The resistance. We can find the resistance of the voltmeter. So the resistance of the meter will be the voltage by the current. So we'll have 4.3 volts divided by 200 nanoamps. So we'll have 4.3 volts divided by 200 amps. And the resistance will be 21.5 mega ohms. So in order for us to get a 4.3 volts reading against a 7 mega ohm resistor, the internal resistance of that voltmeter must be 21.5 mega ohms. The resistance. We can find the resistance of the voltmeter. So the resistance of the meter will be the voltage by the current. So we'll have 4.3 volts divided by 200 nanoamps. So we'll have 4.3 volts divided by 200 amps. And the resistance will be 21.5 mega ohms. So in order for us to get a 4.3 volts reading against a 7 mega ohm resistor, the internal resistance of that voltmeter must be 21.5 mega ohms. The internal resistance of that voltmeter must be 21.5 mega ohms.